All right, let's dive in. Today, we're going to make the invisible visible. We're talking about magnetostatics, those steady, silent forces that are, well, pretty much everywhere, from the compass on your phone to the way your hard drive remembers data. And to get started, let's look at a picture I bet you've seen 1,000 times. Yep, it's the classic bar magnet from science class, with all those beautiful lines swirling around it. But here's the thing, those aren't just lines in a drawing. They represent a real physical force field, an invisible architecture. So what is this thing really, and what's actually creating it? To get to the bottom of that, we first need to get a handle on the space around the magnet, that invisible force field. So, that area of influence, that's what we call a magnetic field. And those patterns we saw, the lines, they're called magnetic lines of force. Now, you can't actually see them, of course, but they're a fantastic way to map out the direction and strength of that magnetic push or pull at any point in space. It's almost like they're contour lines on a map, but instead of showing elevation, they're showing force. Now, this is where things get really interesting, especially when you compare magnetic fields to electric fields. See, electric field lines can start on a positive charge and just end somewhere else. But magnetic lines? Nope. They always form closed, continuous loops. They come out of the North Pole, loop around into the South Pole, and then, and this is the important part, they keep going right back through the magnet itself. This tells us something absolutely profound. You can never, ever have a North Pole all by itself. They always come in pairs. So wait a minute. If you can't isolate a magnetic pole, then what is the real, fundamental source of this whole magnetic field thing? Well, the answer turned out to be one of the biggest game changers in the history of physics. It's all about electricity in motion. That's right, it's wild, but it's true. Every single time an electric charge moves, I'm talking about current in a wire, an electron spinning in an atom, you name it, it generates its own magnetic field. And we even have this awesome little trick to figure out its direction, the right-hand thumb rule. You just point your thumb in the direction of the current, and the way your fingers curl, that's the direction of the magnetic field wrapping around the wire. Simple, but so powerful. Okay, so to actually measure these fields, physicists use two main concepts. The first one is called magnetic field intensity, and we call it H. The best way to think about H is as the raw cause, or the pure effort. It's the magnetic field that's being created directly by the moving charges before the material it's in has had any chance to affect it. And the second concept is magnetic flux density, or B. So if H is the cause, B is the final effect. It's the total density of all the magnetic field lines packed into a certain area, and it includes how the material itself is responding. This is the field we actually measure in units called Tesla, and it's the B field that produces the force we can actually feel. So how do they connect? It's a beautifully simple relationship. B equals mu times H. That Greek letter mu stands for permeability, and all that means is it's a measure of how easily a material lets magnetic field lines pass through it. A material like iron has a really high permeability. It's like a superhighway for magnetic field lines, concentrating them and creating a massively powerful B field from a relatively small H field. Okay, so we've established that moving charges create magnetic fields. But how can we calculate the exact strength and shape of that field for, say, a weirdly shaped wire? Well, for that, physicists have two incredibly powerful tools in their toolkit. First up is the Biot-Savart law. Now, this is the universal brute force method. It basically says that if you want to find the total magnetic field at a single point, you have to look at your wire, chop it up into a bunch of tiny little pieces, calculate the field from each piece, and then add them all up. Yeah, it's meticulous, but the amazing thing is, it works for any shape of wire you can imagine. And you know, this law is basically the magnetic cousin of Coulomb's law for electric fields. They're both inverse square laws, which just means the field gets weaker with the square of the distance. But there's one huge difference. An electric charge is just a thing, a scalar. But a current element, that little piece of wire, it has a direction, a vector. And that makes the magnetic field a whole lot more complex, geometrically speaking. So adding up all those tiny pieces sounds? Well, it sounds like a mathematical headache, right? It makes you wonder, for problems that have a nice, clean symmetry, isn't there some kind of shortcut, like a cheat code? And the answer is a big, resounding yes. It's called Ampere's law, and it's just beautiful. It gives us this really elegant shortcut. It says that if you draw any imaginary closed loop, The total amount of magnetic field you find along the edge of that loop is directly tied to the total amount of electrical current that's poking through the middle of it. Let's take a long, straight wire. Trying to calculate its field using Biot-Savart involves some pretty gnarly calculus. But with Ampere's law, you just draw a circle around the wire, apply the law, and boom. It practically gives you the answer in one line. It is the absolute perfect tool for a symmetrical job.
All right, so we've seen how currents create fields. But let's flip it around. What happens when we take different kinds of materials and put them inside one of those fields? How do they react?
Well, they basically react in three main ways. Diamagnetic materials, like water or copper, they actually push back a tiny bit. They're weakly repelled. Paramagnetic materials, like aluminum, are weakly attracted. But then you have the superstars, ferromagnetic materials like iron, nickel, and cobalt. They don't just get attracted, they dramatically amplify the field passing through them.
And these ferromagnetic materials have this other amazing property called hysteresis. This loop here shows that how they respond depends on their past. Once you magnetize a piece of iron, it actually remembers it. It stays magnetized even after you turn off the external field. This magnetic memory is exactly how we make permanent magnets, and it's the fundamental principle behind how we store data on things like hard drives.
So we've covered fields, sources, laws, materials, all these different pieces. But the real magic, the true beauty of all this, is seeing how all these pieces click together into one of the most elegant and powerful structures in all of science. See, things like Ampere's law, or the rule about magnetic field lines always being loops, they aren't just random standalone facts. They're actually crucial clues pointing to a deep, fundamental connection between electricity and magnetism.
And here it is, the grand unification. These are Maxwell's equations. Just four compact equations that describe all of classical electricity, magnetism, and even light itself. This is, without exaggeration, one of the greatest intellectual achievements in human history. And take a close look. Two of these four pillars should look really familiar by now. The one on the left there, that's just a more complete version of Ampere's law, relating a curling magnetic field to the current. And the one on the right, that's the fancy mathematical way of saying what we figured out at the very beginning. There are no magnetic monopoles. The field lines always form closed loops. You know, we started this whole journey with static magnets and steady currents. But what Maxwell's full theory really showed was this incredible symmetry. We've seen that moving charges, basically a changing electric field, create a magnetic field. So that leaves us with one last huge, tantalizing question. Could the reverse be true? Could a changing magnetic field in turn create an electric field? The answer to that question, well, it changed everything. Thanks for joining me.